Semiclassical general relativity dictates strict constraints for quantum information. Consider a specific configuration inside anti-de Sitter space, or ADS3, a 2-to-2 scattering event positioned completely within the interior bulk. We map two input signals originating in the past at points C1 and C2. These signals meet, interact, and propagate to two output points, R1 and R2, in the future. The defining physical constraint of this setup is isolation. The entire sequence, the inputs, the collision, and the outputs, happens strictly inside the bulk geometry. The signals never reach the outer boundary shell. If holographic duality demands that the boundary theory perfectly mirrors the bulk, we face a distinct mechanical problem. We have a local scattering event occurring entirely out of causal contact with the boundary. We need to explain how the boundary can encode information about an event it cannot physically touch. On this 3D cylinder, we define diamond-shaped boundary regions V1 and V2 by intersecting the input futures with output pasts. This sets up Alex May's connected wedge theorem. The existence of a bulk scattering event forces V1 and V2's entanglement wedges to physically connect. This geometric connection requires a mathematical translation. A connected wedge establishes a hard lower bound on the boundary mutual information, specifically scaling as order 1 over Newton's constant. The topological rules of bulk spacetime dictate a minimum threshold of quantum entanglement resources on the dual boundary. To evaluate this connection, we project the boundary regions into the bulk using HRT surfaces. For isolated boundary regions, these extremal surfaces bow slightly inward as entirely separate, disconnected geodesic arcs. While isolated in this disconnected phase, the boundary regions V1 and V2 operate independently. Their mutual information evaluates exactly to 0. We measure the transitions between these states using the principle of superadditivity. When subregions combine, their joint entanglement wedge can access a larger portion of the bulk than the sum of their individual wedges. The phase transition itself is a strict minimization problem. A connected wedge forms when the total area of a single bridging HRT surface drops below the combined area of the disconnected candidate surfaces. Once connected, the unified entanglement wedge penetrates much deeper into the space, directly encompassing the central scattering region. Because superadditivity assigns this deeper geometric access, proving the wedge is connected proves the mutual information between V1 and V2 is strictly greater than 0. We map the specific architecture of this space by layering the bulk causal regions. First, we identify the pure bulk scattering zone, R points, which is the literal intersection of the light cones from our input and output points. Next, we map R regions. This larger causal diamond is generated by the futures and pasts of the boundary regions themselves, perfectly encapsulating the inner scattering zone. Finally, we define R entanglement, representing the exact intersection of the full boundary entanglement wedges, which engulfs the previous two layers. We refer to this nested structure as a metric doll topology. The physical requirements that form the innermost scattering point inherently guarantee the existence of the larger causal containers wrapping around it. The boundaries enclosing these specific geometries are formed by intersecting null hypersurfaces, commonly referred to as light sheets. By tracking the outer light sheets, we locate a highly specific anatomical feature, the ridge. This line is the exact seam where the future-directed light sheets originating from V1 and V2 collide. This topology isolates the exact geometric boundaries and intersection points required to execute a formal mathematical proof of the area transition. We isolate a single light sheet propagating upward toward that intersection ridge. This equation, the Ricci-Choudhury equation, allows us to measure exactly how this light sheet behaves as it moves through the geometry. Here, theta represents the expansion scalar of the surface, and Ka is the null vector field generating that expansion. We apply the null energy condition, establishing the foundational positivity requirements for matter in this spacetime. Because our specific congruence of light rays is hypersurface orthogonal, the shear term in the equation drops precisely to 0. This leaves a simplified inequality. The rate of change of the expansion, with respect to the affine parameter, must be less than or equal to 0. We evaluate this against our initial condition. The light sheet originates at an extremal HRT surface, meaning its starting expansion is exactly 0. If the expansion begins at 0 and its change is negative, the scalar becomes strictly negative as light flows forward. Translated into physical reality, gravity forces the cross-sectional area of these light sheets to shrink as they travel up to the ridge. This split layout compares the competing geometries. On the left side, we calculate the combined area of the disconnected, boundary-anchored extremal surfaces. On the right side, we calculate the secondary areas, defined as the bulk ridge plus the 4 connecting segments. Our null focusing derivation establishes a hard constraint. The area of the starting surfaces must be greater than or equal to twice the area of the ridge, plus the segments. Because the ridge geometry inherently structures the connected configuration, this inequality proves the connected wedge mathematically possesses a smaller area than the disconnected candidate. We apply the Ryu-Takayanagi formula to translate this geometric area differential directly into quantum entropy, dividing the area by 4gn. The mechanical focusing of light sheets in the bulk forces an order 1 over gn lower bound on the mutual information between the boundary regions. We can verify this geometric requirement by analyzing it through the lens of quantum information protocols, specifically quantum tagging. If you attempt to spoof a non-local communication protocol to perfectly mimic a local bulk scattering event on the boundary, you must consume massive entanglement resources. That informational cost scales exactly with our geometric lower bound. We can also execute the inverse operation. By reversing the focusing direction, projecting light sheets from the complementary regions instead of the primary ones, the topology yields a different constraint. This inequality visualizes the result, drawing on Raphael Busso's work with generalized entropy and the definitions of max and min wedges. By evaluating the complementary regions, the reverse focusing establishes a strict upper bound on the entanglement wedge, placing a ceiling on the mutual information. Together, these upper and lower bounds prove that classical bulk geometries lock quantum information quantities into a highly constrained mathematical window. Standard ADS-CFT correspondence models rely on a clean, well-defined boundary wall, a feature our actual universe lacks. The objective of flat space holography is to push the Cauchy slices of the space out to space-like infinity, effectively erasing that boundary wall entirely. The connected wedge theorem is highly relevant to this problem because its mathematical engine relies entirely on bulk geodesics and internal light sheets. The logical proof survives even when the specific boundary definitions are removed. As research expands into the mechanics of flat space quantum gravity, the semiclassical rules of general relativity provide a rigorous mechanism to map bulk physics to holographic information.